Okay, so anyway, how many objects do you see there? I see B. What do you see? 3 pulleys. Good. So a pulley hanging off a B, a C pulley, a D pulley, and a hand. And there's also a rope there, right? How many ropes? 2 ropes? 2 ropes. Okay. I'm going to count the degree of freedom of this thing. Okay? So what I'm going to do is I'm going to ask myself, is it physically possible that something could be moving? Yes or no? Yes. What could be moving? The weight, okay. I heard hand. I'm going to work on hand, and then I'll do the others, okay. But you just have to find one thing, right? Doesn't matter which one you find. I'll do it in a couple of ways. Okay, the hand is moving. You all agree? Because it says I'm moving down by blah, 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 blah. Okay, so the hand is moving. I count 1 degree of freedom for the hand. And now I pretend like the hand doesn't move. Pretend like the hand doesn't move. Can anything move? No? Can it swing back and forth? Why not? Well, you know, this is an easy problem. It's a homework problem. They don't swing things back and forth. What if you were in the real world? Maybe it does, right? Maybe it does. And if the thing were swinging back and forth, you as the engineer would have to say, well, the swinging is so small, I don't think anybody's going to worry about that. I'm not going to worry about it. Okay? So in the real world, when you're counting degree of freedom, it's a tool to help you think straight about what you're going to include and what you're going to exclude. Okay? Most of these homework problems that you see in the book, they're fairly simple. Things don't swing. Does the rope break? Well, if the rope could break, there'd be another motion, right? Get the idea? In the real world, you'd have to say, well, I'm worried about that rope breaking. Are you worried about the rope breaking? No? Is it physically possible that this rope right here could go slack? Well, if you were in the real world, right, and it's in an elevator, and man, you went down really, really fast, couldn't it go slack? Okay, you think that's what's happening here? No. Okay, so in textbook problems, they're fairly simple. Oh, yes, 1 degree of freedom, can't be anything other than that, right? When you're the engineer practicing doing something, you have to ask yourself, is it possible that this rope could go, well, is it on an elevator? No, it's tied to the roof. Well, come on, man, barring any catastrophic failure of the roof, ain't nothing going to go slack. You get the idea? Okay? So the degree of freedom in the real world could be you have to kind of scratch your head and go, what do you want to worry about? Now, 1 degree of freedom. Make sense? 1 degree of freedom. Okay. What does 1 degree of freedom mean? What does n degrees of freedom mean? Here's what it means. Okay? What it means is there is one and only one motion that needs to be known. Right? What's motion? You know. It's a velocity. It's an acceleration. It's a position. One and only one that you need to know. If you know it, you know the motions of everybody else that's in there. Everybody else. Do you need to know gravity? Do you need to know? If you know the one motion, you can find all other motions. That's what 1 degree of freedom means. Got it? Okay. So I'm going to look at this thing and I'm going to say, man, I don't know what I'm supposed to do with this. They want me to find the speed of block B. What are they telling me? Speed of the hand? Right? Over here they say, find the speed of block B. And what they tell me is the cable is pulled down, so the speed of the hand is 2. So here's what's happening. This 1 degree of freedom, they're telling me that this one motion is 2 downward. And they want another motion. You see that? Could I get them? Yes, you can, because they've got to be related to each other. The motions have to be related to each other. They have to be. So block B has got to be related to block A. That's what I know because of the degree of freedom. And you say, you're beating a dead horse. Yeah. But in the real world, this is what you do. You say, what's the degree of freedom? What does it mean? It means 1. You give me one motion, I got them all. That's what it means. May be hard to get them, but I can get them. Oh, I hate that tablet. Okay, so How do you get them? Well, they're related somehow. And in this particular case with ropes, I haven't done a whole lot of work in the real world with ropes, but they're similar. Okay, with the ropes, how many ropes did you say I had? 2? I'm going to write down the length of 2 ropes. I'm going to say rope 1 that goes around from the hand and around there. I'm going to say the length is boom, 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 whatever. And then I'm going to write down the length of the other one. That's what I'm going to do. Okay? I always do that. Okay, so here we go. Let me erase this stuff. Okay. Let's draw a little picture of this thing, if I can. There's the pulley D. Here's the hand. I'm going to just put a little dot there. Pulley D comes around or wraps around C. C comes off the middle, wraps around D. And this guy hangs down from here. Bless you. So that's kind of what's going up there, right? Do I see that? Right. So this is block B. This is, well, it's not labeled, but this one is C. And this one up here is D. I'm going to call this guy right here H for hand. Everybody okay with that? All right. Now what I'm going to do is I'm going to establish a coordinate system and measure distances to these things. Okay? So what I'm going to do is I'm going to choose the roof to be the origin. And I'm going to measure everything positive downward. Is that okay? Okay? So this would be positive distance right here. Now, how long is the rope that goes around C, D, and H? L. Okay, you're right. It's L. Give it to me in pieces. How far is it from the roof? From here down to here. How long is that? Gee, if I only knew where C was, you could tell me, right? If I told you C is 10 feet down, couldn't you tell me, oh yeah, it's 10 feet? So whenever I say, oh, if only I could, I define a variable. What variable you want me to call this? Position of C? I didn't quite hear what you said. Does that make sense? I'm going to call the distance from the roof down here to this pulley the position of C. So how long is that little piece of rope? XC? Okay, so we're going to call it XC. So the length of the rope is XC. And then if you notice, a little bit of rope goes around the pulley. See that? Does it change? Okay, so let me call it a constant. So, okay, I'm going to just call it C. Okay. Plus a little bit around the pulley. I'm not going to have heartburn about constants because what I'm going to do is differentiate this, and all the constants are going to disappear. Okay, how about the length of rope between here and here? How long is that rope? C plus D? Is D fixed or is it moving? It's fixed, are you sure? D. D is in dog. Absolutely. Yeah, because if you notice, the distance between here is tied down, right? The distance between here and here is constant. So it's C, position of C, minus a constant. Is that right? Okay, so I'm going to write that down. So the plus position of C minus a constant. And since I'm not too worried about the constants, I'm just going to say C, 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 because when I differentiate them, all the constants are going to disappear. So why give them a special name? I'm going to wipe them out anyway. Okay, so I'm not going to have an ulcer over it. Okay, is there more rope? Goes around the pulley D, doesn't it? Is that a constant? Okay, so I'm going to just add on a C. It's a different C, but who cares? Name it if you want to. What's left? Is there any more rope? Yeah, the length from there to where? To the hand? Do you know how far that is? Well, if only I knew where the hand was. Well, then what does that tell you? Define a variable. Okay, we'll call it, let's see, we're calling them X, right? XH for hand. Okay? And the way it's shown, it's a positive amount, right? Because it's coming down from the top. So this would be plus XH. Okay, is that the end of the rope? No more rope, right? So that equals, we'll call it rope number 1. Is that good? Is rope number 1 constant?
Yes.
Okay, so they're looking for velocity, so what I'm going to do is I'm going to differentiate this. Right? I'm going to differentiate it. Okay, so when I differentiate it, what's the derivative of xc? Velocity of c, vc. Let's call it velocity of c, yeah? dx dt equals v. Okay, so this would be velocity of c. What's the derivative of that constant? 0? You got another xc. What happens when I take a derivative of it? Another vc plus vc. Minus a constant. What's the derivative of a constant? 0 plus a constant. What's the derivative of a constant? See how it works? It's like, man, holy cow. Here's an xh. Take a derivative of that. What do you get? Velocity of h plus vh equals. What's L1? Constant? What's the derivative of L1? 0. How many equations do I have? Well, I've got one for velocity. Right? That's what I'm looking for is velocities. I've got one equation for the velocity. How many unknowns? Or how many variables? 2. Okay. Do you know any of these? What do you know? The velocity of the hand is 2. Is it positive 2 or negative 2? How do you know it's positive 2? It's going down. Aha! I said down was positive. You're right. Down was positive. I could have done it the other way, but then everything would have flipped signs. But down was positive. It's going down by 2. Bless you. So I'm going to put in a positive 2 for VH. So what is VC? Yeah, exactly. Just go ahead and solve it. 2VC plus 2 equals 0. So VC equals what? Negative 1. What does that negative tell you? It's going up. Does it make sense? How can that make sense? If this guy right here, if you pull 2 feet on this A, then this rope right here between D and the hand, isn't it 2 feet longer? Where does that 2 feet of rope come from? Well, some of it comes between here, and some of it comes between here. Half from each one, doesn't it? So the 2 feet that you pull here has to take up a foot between C and D, and it's got to take up a foot between C and the roof. See how that works? Now, it's okay for you to say, look, you know, I'm clever at this. I'm going to pull this down. And that's okay. You pull this down at 2, and you can ask yourself, what does this do? Perfectly okay. And there's a lot of books that will teach you to do that, right? Kind of using your logic. What I have found is my logic fails me more times than anything, right? So I want a system that I can plug in and go. And so what I do is I add up the length of the rope. Okay? It's up to you. If you say this is ridiculous, I can get it faster, hey, more power to you. Okay? And the book has a different way of doing it too. So if you don't like my way, look in the book. Okay? But in class, this is the way I'm going to teach it. Okay, that's not really what I wanted. I know what C does. What did I really want? B? Okay. So could I get B? Should I have confidence that B can be obtained? Why? Okay. I won't argue with that. That's good. But my answer is it's 1 degree of freedom. Of course you can do it. Right? I mean, but you're right. You're exactly right. But because it's 1 degree of freedom, it means if you tell me one, I can get all the others. So I have absolute confidence it can be gotten. Can be gotten? Gotten did? Can be getting. Okay, so anyway, obviously, I did take English, but I forgot it all. So anyway, let's go and do it. How in the world am I going to do it? Well, I have another rope, right? You said there were 2 ropes? All right, let's write down the second rope equation. Okay, we're going to write down the second rope. In fact, you write down the second rope equation. How long is the second rope? Write it down, and then, okay, it'll still be recorded, but you won't be able to see it. So write it down, and I'll write it down, and then I'll turn the monitor back on. Okay, everybody know what we're doing? Okay, we are writing, I got to turn it back on now. Okay, we are going to write the length of the second rope. Come on. Well, that was a bad idea. Yeah, okay. All right, so let me sketch out the picture. It goes like this. There's a rope comes off the ceiling, comes down and loops around, and then connects up to C. And this guy right here hangs the block. So we'll call that block B. How's that? This is the second rope. I want to know how long he is. How's that? Now do you know what we're doing? Okay. And I'll try not to be clever, but just don't peek up here. Do it yourself. Don't peek up here. Do it yourself. Don't peek up here. Hey, stop looking. Do it yourself. I mean, that's what you need to do. You need to do it, and then you can see if you're right. Bless you. Okay, did y'all get it? Does it look anything like this? What's the distance from here, from the roof down to here? XB, okay. And if you say, oh, no, XB goes down to the block, okay, well then it's XB minus a constant. Either way, right? So if you say, look, I got to have those constants, that's fine, but don't get hung up about them because they're going to disappear, right? So even if you say, well, it's XB all the way down to here, and then I'm going to subtract off a constant, that's fine. So it's XB minus a constant. So far, okay? And then, what's this distance over here, from here to there? Yeah. Right, so you go down to B and then you back up to C, right? And that'll get you that little piece of rope. There, is that okay? Beg your pardon? And then there's a little bit of rope around this guy right here, which is a constant. And maybe a whole bunch of other constants. Because you say, well, look, there's a constant between that hook and the center of that pulley. Yeah, a constant. I don't get ulcers over constants. Right, because I'm going to differentiate them. Okay, so you put in as many constants as you want to make you feel comfortable. All right, now what are you going to do with that equation, you think? Let's take a derivative. Yeah, so let's take a derivative. So let's see, VB plus VB minus VC equals, what's the derivative of the length? Does it change? No? Okay, then it's 0. Okay, so I can plug in, let's see, VC. Did you get VC? -1, meaning it's going up. Okay, so I'm going to plug into this thing, and I have 2VB minus, the minus comes from the formula. Now, what did you say VC was? Negative 1 minus 1 equals 0. All right? Where did that first negative sign come from? This guy right here. From the formula. Where did this one come from? From the number. Right? From the number. So what's VB? I think it's negative. Negative 1/2. What does the negative mean? Yeah, down is positive, so the negative means it's coming up. Does it really come up? C is going up. So should B go up? Okay. Why should it be half of C? Because the equation says so. Okay, but why?
Because C is going to have to pull both sides.
Yeah, so when C goes up 1 foot, okay, if it goes up 1 foot, then this rope right here, right? You need, I can't explain it. You see why I add up ropes? He's got a good head on his shoulders. Ask him. He can see it. If you can see it, that's wonderful. I don't have a problem. What I want is that when you're faced with something like this, you, one way or the other, find out that VB is negative 1/2. It's going up at 1/2. If you do it with my ropes, that's fine. If you do it like the author does, that's fine. If you do it like he does, that's fine. But don't come back and say it's 1/3. It ain't. Got it? Everybody clear? Okay, I like ropes, okay? Or the rope methods, you know, you can do it your way. Just make sure you get them right, okay? Practice them. Is everybody clear on what I'm saying to you? Okay. How about I do another problem? One that's a little bit different. Okay, and then I look through all the other homework problems, and if I do this second one, I think you'll have everything, you will have seen, I think, everything you need for this homework. Okay? So let's do that one. The next one is 200. Okay, this one is kind of a wild looking guy. The motor at C pulls in the cable with an acceleration of, and they give it to me, where T is in seconds. The motor at D draws in its cable. That's what they asked me for, right? The velocity, not the acceleration. I didn't read the 199. Let's see. The motor at D draws in its cable, and they give you that acceleration. Both motors start at the same instant from rest. When D equals 3, determine the time needed from blah, 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 the velocities, da, da, da. Okay, so that's what we're doing. Okay. All right, so let's take a look at this problem and try to figure out what we're expecting that we will have to do. Okay? Because what's nice is if you kind of know what to do, you're not shocked when all of a sudden you have to do that. Okay? All right. So let's start in like we did before. How many degree of freedom is it? 1. I hear 1. 2. I hear 2. 3. 3. Going on 3. 3. 3 once. Going 3. It's either 1 or 2. It's 2. Okay, well, let's find out, right? So I would ask you, can something move? What? Okay, give me 1. A. Okay, A moves. All right, so if A moves, that's a degree of freedom. Everybody see that A could move, right? Because you're winding up this, I always want to point at the thing. I'm winding this guy up, and so A is going to move. All right? Pretend like A is not moving. Okay, so you count 1. Pretend like A is not moving. Is it possible that something could still move? B. Okay, so that's 2 degrees of freedom. Stop B. Stop A. Stop B. Can anything move now without breaking? Okay, C. How could C move and not break something? Your whole... Okay, well, let's see. You're going to hold down A, right? A can't move. So this pulley can't move. The rope is tied over there. If C tries to move, what happens to the rope? It breaks. We don't break things when we're counting degree of freedom. So no, C. If you stop A, C has to stop too. It cannot. I mean, it'll be right, but it can't move. See that? What about, same thing applies to D, right? So it would be 2 degrees of freedom. What does that mean, that it's 2 degrees of freedom? Oops. Man, I hate this stupid. Man, for some reason, all my colleagues, they say, I can't get the screen to da-da-da. Oh, and they do it. I cannot get the screen on an Apple to do anything for me. I think it's because it knows that I hate apples. Okay. I don't know. I'll figure it out in a minute. It's either that or my handshakes. One of the two. I don't know what the problem is. Okay, 2 degrees of freedom. What does that mean? It means if you give me 2 motions, I can find all other motions. Do they give me 2 motions? Yeah, what are they? Yeah, they give me the acceleration of the D and the acceleration of C. Right? I'm pulling the ropes in at those 2. Okay, 2 degrees of freedom, 2 motions are given. I can find all motions. Okay? Just like I did before. I can find them. Okay. In this particular case, 2 degrees of freedom. How many ropes you got? 2. So you're going, normally then what you would do is you write the length of 2 ropes. You know you're not done until you write the lengths of those 2 ropes. Okay, so the next thing is something we hadn't talked about. Problems in dynamics can either be time spanners, and this is a terminology I've invented because the books don't define them. But I'm telling you, after 30 years of doing this, it comes in really handy. There are time spanners and problems that do not span time. For example, the last one we had was a non-time spanner. Look at it. Okay, let's go back and take a look at it. See why that was not a time spanner. It says this guy is being pulled down right now, this. What is the speed of that? What they're saying is right now, this is happening. What's that guy doing right now? You see that? So it's at this moment, instantaneous. You see that? What about this one down here? Is that what's happening? No, this is different. It's saying at this moment, they start from rest. They are right here. Something happens. Tell me what it's doing when that thing happens. You see, time has elapsed. Got the idea? Now, it's important to recognize these because there will be 2 distinct ways that you're going to attack dynamics problems. When you have a time spanner, typically what you will do is you will calculate the acceleration of something, and then you will integrate it, right? The acceleration will be a differential equation, and you will solve the differential equation. And you've done that in this class. You've separated variables, or you've used those handy-dandy formulas from Chapter 12. Okay, so this is a time spanner. What do you think you're going to end up having to do? You're going to have to integrate. So expect it. Okay, expect it. Okay, so it says the motor at C pulls in the cable with an acceleration where t is in seconds. The motor at D pulls in at so-and-so. If both motors start at the same instant from rest, in other words, initial velocities are all 0. In this location, if what's the time needed and the velocities when B slips 3 feet or 3 meters? Okay, how in the world are we going to do this? They're asking me something about position. When do you go 3? And you're saying, ain't nothing goes 3. Well, yeah, they're right, but right? They want position. And they're telling you acceleration. And it's a time spanner. So what do you think you might do? Get the yeah, so what yeah, exactly. Since it's a time spanner, typically I'm going to go get the acceleration. And then I'm going to integrate the acceleration and get the position because I know something about the position. Does this ring a bell from the old Chapter 12 stuff that you already took a test on? Yeah. I kicked the ball here, you knew gravity, and then where did it land, how long did it take, blah, blah, all those things. Now this one looks weird, I understand. This one looks weird, but it's the same thing. Right? It's the same thing. You agree? Okay, let's see how to do it though. That's the real trick, right? And, aha, okay, now, how do I get a new page? There we go. Fresh page. Okay, so this is 12,200. All right, so how would you start? You need to know something about the position of A and B, right?
Well, we know the acceleration of the acceleration. AC.
Okay, so, yeah, right, so what I'm going to do, I want the position of A and B, I want the acceleration of A and B, and then I'm going to integrate the acceleration of A and B, and I'll know where they are. And I think that's what you're saying too. Does that make sense? Okay, so here's what we're going to do. Get me the acceleration of A and B. All I have is C and D.
Would the acceleration of B just be acceleration of B?
It will, but I'm gonna do it in a fancy way. So you understand it, right? Hang on to that. But I'm gonna do it in a standard way because I don't think like you think. Okay? Here's what I'm thinking. I want the accelerations of A and B because it's a time spanner. I want the accelerations of A and B. Then I'm going to integrate them, get the positions, and then I'm going to somehow equate it to 3. That's where I'm headed. Okay? So the question is, how do I get the acceleration of B? And now I panic and I go, oh my goodness, could it be done? Yes, it can be done. Why? Because it's 2 degrees of freedom, and you've given me 2 other accelerations. There has to be a relationship, and he already knows it without even writing an equation. So he should be teaching the class. Right? Well, seriously, I mean, talk to him a little bit and you say, oh man, that makes a lot more sense than whatever it's making us do. That's fine. Hey, that's fine. Just be able to do it. Okay? I don't care how. Be able to do it. 2 degrees of freedom. I know I can do it. Okay. What do? I write the length of ropes. That's what I do. Right? Because I'm not that bright. I got to do it the same way every time. Okay, I'm going to write the length of ropes. All right, how about we work on rope that's connected to A. Is that good? Okay. I'm going to define an origin and a direction. I would like to choose the right wall, not the correct wall, the right wall, and measure everything positive left. Is that okay with everybody? It kind of makes sense to me. So the right wall and over. Okay, so so let's see, I'll try and draw a little box. Here's the top box, here's the A box. So here's the right wall. And I have a rope that comes off, loops around there, and comes back with a pulley, or a motor, excuse me. Okay, so this is positive. All right, how long is that rope? Is how long? The rope that connects to A and C. Is it just one XA? Okay, but isn't C anchored down? Right? Isn't the distance between here and here a constant? Yeah, so I would say XA, right? Plus, here's another XA minus a constant. Does that make sense? Right? Because it's anchored down. Now, do you lose sleep over constants? No. Okay. So I'm going to say it's XA plus XA plus or minus some constants. Is that good? Do you agree with it? XA plus XA plus or minus a few constants. Got it? Now you're saying, yeah, but the rope is being pulled in. I'm not talking about the rope being pulled in. I'm just saying right now, how long is it? Right now, how long is the rope? That's all I want to know. Okay? So I'm going to write that down. So it's XA plus XA plus or minus a few constants. And what does that equal to? We're going to call that rope 1. Is that good? And I'm looking for acceleration, right? Okay. If this is positions and links, if I take 2 derivatives, I'll get acceleration. Yes? Okay. What's the second derivative of that? Can you do it real quick in your head? Yeah, you have a question?
It's not XA plus XA minus C?
Yes, it is. And the distance between C, right? XA goes from here to the wall, right? You can see my mouse, right? So A goes from here to the wall. What's this distance between there and the wall? Does it ever change? Yeah, that distance doesn't change, right? So you're right, but it's XA plus XA minus a constant. We don't worry about constants. They're going to disappear. Okay, can you quickly in your head take the second derivative of that? Okay, you just put a double dot on everything, right? Okay. So, comma. Okay, here we go. That would be 2XA double dot plus the second derivative of a constant, 0, equals second derivative of L, 0? Is the rope constant length? Careful, is the rope constant length? What's the motor doing? Pulling it in, isn't it? So the derivative of L is not 0. It's being pulled in. Right? It's being pulled in. Does it tell me how much it's being pulled in? How much? 3t squared. Okay, so I say equals 3t squared. That's the change. Whoops, oh, I'm sorry. Whoa, whoa, that's it. No, that's the, that is the, oh, that's the acceleration. You're right. Good. I had to read it a little closer. That is the acceleration. That would be L double dot. Is it positive or negative? Yeah, because the rope is getting smaller, right? Isn't it? Okay, so it's negative because the rope is getting smaller. Does that make sense? That as time goes by, XA double dot is actually a negative? It's accelerating to the right? Really? Absolutely. If you're yanking that cable in, man, it's going to be coming towards you big time, right? And I chose left to be positive. He's being pulled that way. He's got a negative acceleration. How much? Negative 3/2 t squared, right? And he probably already had it. And it's okay to do it in your head. It's okay, all right? I'm not going to take off because you don't write the length equation. I'll take off because you write down the wrong answer. That's what I'll take off for. Okay? So when in doubt, you write down the length equations. Okay, you got another rope? Okay, let's write down it. Okay? And I like to keep the right-hand side and measure it over. So how long is that rope? XB? Is it XB? Maybe. I'm confused. I'm really confused. So here's what I was thinking when I did this. I said, well, you know, I'm kind of confused, but I think the length of the rope would be something like this. It'll be the width of that channel, right? From one side to the other, from there to there, right? So it'll be the width of the channel, which is a constant. I'm just trying to get my head around it, right? Okay, width of the channel minus the position of B equals the length of the rope. So what I'm doing is I'm measuring from here all the way over to here, and then I subtract off this blank distance right there. And is that the length of the rope? Maybe minus a constant from the box, the width of the box maybe. That's how I did it. That made sense to me. Does that make sense to you, or would you write it some other way?
I'm sorry, can you explain it one more time?
No, I doubt it. I couldn't do it the first time. Well, you think I'd do it twice. Okay. All I need is the length of the rope. I'm not saying this is the only way you can do it, but this is what I was thinking when I saw that picture. I said, oh, yuck, I don't like these things. So what I said was, I think the length of the rope is the width of the channel, W, which is a constant, okay, W, and then I'm going to subtract off where the box is. And that'll leave me the length of the rope, right? So if I take in this width and I subtract off this distance here, which is the position of B, then I'm left with this thing right here, which is the length of the rope.
Should it be XA or XB?
Should be B, because the rope is attached to B. Doesn't really matter where A is.
So we're subtracting that.
That's what I did. What would you call the length of this rope, this top rope right here?
XB, but
Is it XB or minus XB?
Because we established that the positive CLN, so I could, for me it's.
so we're getting that distance to the right?
What I did, W is from here all the way over to here. And that's too far for the rope. Rope isn't that big. And then the B, let me see if I can draw a picture of it over here. Okay, so here is the channel. Here's the B. And this guy right here is XB. Simply because I like to draw it from the right-hand side. You see? And so, if that's XB. Now, see, I think what you want to do is measure XB from the left-hand side. That's okay, but now you're going to have problems because A comes this way and B goes that way. And when you're trying to put in the 3, you're going to go, oh, man, do I put in plus or minus 3? Right? Not that you can't do it. You just have to think more carefully, right? So I like to put everything the same direction. And then I'm faced with this, well, it's not really X because, right? It's not really X, it's the width minus X. That's how big it is. Okay? All right, so this is equal to the length of the rope. I'll call that L2, comma. Okay? Now, what are you going to do with it? I'm looking for acceleration, so what I'm going to do is I'm going to differentiate this how many times? Twice. Okay, the constants disappear? Yeah.
The C box is the length from the box of B, right?
Beg your pardon?
The C box,
Yes?
it's the length of box B?
Yes. It's just a constant. So if what's happening to you is saying, now wait a minute, he left off the length of the body, he left off the pulley, he left off then throw it in there, but it's constant. So it's going to disappear. So put it in as many as you need. So for example, you could say, well, between A and the center of this pulley is a constant. Yeah, you're right, it is. Throw it in there. So whatever, get your head around it. But don't worry about it because it'll disappear. Okay, so I'm going to take 2 derivatives. Okay, what is the W double dot? 0. What is X double dot? XB double dot? Acceleration? Okay, so this would be minus XB double dot. What's C double dot? C box double dot? 0. So that equals. What is the L2 double dot? The length of the rope 2 double dot. Five. Positive or negative? Is it getting bigger or smaller? Smaller? So this would be -5? The L double dot? Okay. Minus 5. What's the acceleration of B? Positive or negative? Positive 5. What does the positive mean? Going to the left. Does that make sense? Is it really going to the left?
Yes.
Yeah, if you're yanking it in, it's going to the left. Now, this is overkill. Most of you, I bet you, are saying, well, look, any idiot knows that the acceleration of B is 5. Hey, that's fine. On a test, if you got that kind of in gut feel, do it. But one of the problems you have is oftentimes you'll say, well, I know doggone well that's 0. No, it ain't. No, it ain't. And you will get an answer, and it's all wrong. Now, I have done stuff like that, right? I'll be out in the real world, nobody's holding my hand, and I'll say, well, I know that thing is 0. I put in a 0, I crunch and crunch and crunch. 2 weeks later, I get the answer, and the rocket crashes. And I go, huh? What? Well, it wasn't 0. Okay, so be careful. Your gut comes in handy, but your gut can be wrong, right? Your gut can be wrong. So after making a few mistakes, what I've learned is, okay, my gut tells me something, but I'm going to use the math anyway, and when the math confirms my gut, then I say, man, I was a smart guy, right? Rather than the other way around. If the math doesn't confirm my gut, I go, maybe I made a math mistake, which has happened, especially before Mathematica. Maybe I made a math mistake, or maybe my gut is wrong, right? So, and I don't turn it in until I resolve it. Say, oh, stupid me, it doesn't go left, it goes right. Oh, right? Because you make mistakes. So what I'm telling you is use your gut. That's what makes you a good engineer, but be careful, right? All right. So now I've got these two accelerations. Now what? They're telling me something about the positions, right? It's a time spanner, right? What are you going to do with the accelerations now that you have them? I'm going to integrate to get what? Position, right? Oh, and they're also interested in velocities. So let's integrate them, get the velocities. Let's integrate them again and get the positions. Okay, how do I know to do that? Because it's a time spanner. Why did I use the ropes? Because they didn't tell me the acceleration of A and B, they told me the ropes. So I had to use the degrees of freedom stuff to get the A and the B. Now that I have the A and the B, what do? It's a time spanner. I'm going to integrate them. That's what you always do on time spanners, okay? So here we go. Let's get the first one. You all do it. Right, so XA double dot is equal to minus 1.5 t squared. So what this means is dv dt is equal to minus 1.5 t squared dt. And then you're going to integrate, right? Separation of variables. You're solving a differential equation. You separate the variables. Can you integrate that? I bet you can. If not, open up Mathematica. It can. So what do you get? You get velocity. Velocity of A equals, let's see, minus 1.5 t cubed over 3 plus a constant. Right? What's the constant? How do you find it? Initial. You always find them with initials. It doesn't have to be initial. I could say you're doing 100 miles an hour in 1 hour. Okay, you have to have a condition, but they're usually initial. Okay, what was the initial condition? How fast was it going at the beginning? 0. It started from rest. Okay, so what's C? 0. So VA. So I got a VA. Let's go ahead and get the XA. Right. So the XA and so I'm going to do separation of variables just like before. Okay. So this would be, let's see, 1.5 over 3 is 0.5 minus 0.5 t to the 4 over 4 plus another constant. How do you find that other constant? Initial conditions, it is 0. What we'll do is we'll say, okay, where it starts, we're going to call that the origin. So C1 is equal to 0. Okay, so I have position A, velocity of A, which I'll use in a little bit. How about velocity of B and x of B? Can you get it? Do you need to integrate it? Or do you have something else? It's a constant, so you can use all those formulas that you just took a test on. Right? They work whenever there's a constant acceleration, right? Okay, so let's just write that one down. Okay, velocity of B equals the initial velocity of B. How much is the initial velocity of B? 0. Plus acceleration of B. What's the acceleration of B? Negative? 5. 5 times t. Can we get the position of B? xb equals, what's the initial xb? Let's call him at origin where he starts. Is that good? You could do 3, I guess. I'm gonna, because I want to bring something else in. I'm going to say he starts at the origin as well. Right? Wherever he is, he's at the origin. What's his initial velocity? 0. Okay, so it's plus 1/2 at squared. 1/2 a t squared. The handy dandy formulas, right? For positions, 1/2 at squared. A is 5, so 1/2 of 5 is 2.5. Okay, now what am I going to do? Well, I say, okay, now that I know where everybody is, I'm interested in a special place. What I'm interested in is when B slides on top of A 3 feet. Right? So here's the deal. I would say that B relative to A, and this is why I did it this way, B relative to A is equal to 3. B relative to A. What in the heck does that mean? Here's what relative means. When I say your speed relative to the earth, okay, what that means is you stand on the earth. We're doing that. Y'all are sitting on the earth, but you stand on the earth, right? And you look around and you see how fast or something's going. Okay, so my lunch right here. Okay. What is the velocity of my lunch? Relative to the earth. What is it? 0. What is it really? Yeah. I mean, what's the circumference of the earth? 24,000 miles or something? Whatever it is, it goes that distance in one day. And that, I'll tell you, that's fast. So that lunch is going pretty doggone fast. But relative to the earth, what's it doing? Nothing. Okay, so here's what I'm saying. All right, I want you to stand on A. Pretend like you're standing on A. And you look over there at B. What am I looking for? I'm looking for B to move 3 feet. Right? So here we are. We're on the earth. I'm looking for this guy right here. And you tell me when it moves 3 feet. There you go. Get the idea? Okay. So that 3 feet, because things are moving crazy, I say, okay, look, tell you what, man, I don't know where anybody is, but here's what I know. Stand on A. Right? Just like you're standing on the earth. Do you see yourself moving? I mean, you probably wouldn't be here, you'd be in your hospital somewhere. You get the idea? Now you see the sun going around. As the sun does move. Right? In the old days, they thought the sun moved, didn't they? Right? So you look around and you can definitely see things. You get on a merry-go-round and you look at the ground. What does the ground look like it's doing? Man, the ground is moving all of a sudden. You look down at your feet, you don't look like you're moving. You get what I'm saying? All right, so what I want you to do, whenever they have these weird motions, stand on one of them. So I want you to stand on A. And I want you to watch B. And I'm interested at a particular moment, and that is when you see B move 3 feet, or 3 meters. That's what I'm interested in. Is that clear? Okay, so now all I have to do is say, well, you did read the section 10 on relative, yeah, right. So I need to define relative. Here's how you define relative. It's not that hard. Relative motion. So velocity of one thing, let's say B, relative to the velocity of A. That is the velocity of B minus the velocity of A. It's that simple. If you want B relative to A, it's B minus A. If you want A relative to B, in other words, I'm standing on B, looking at it's B relative is B minus A. Okay? It's that simple. Okay, so here's what I want then. I want to know what is the position of B relative to A. And what your book writes, this is the way your book writes it. They'll write V, B, slash, A. And so you have to remember what that slash means. And here's how I remember it. You can remember it any way you want. I think of it as I'm going to stand on the lower subscript, the slash. I stand on the guy down below and I kind of look at or reach for the one above it. That's the way I remember it. So when somebody writes VB slash A, I go, huh, what? I stand on the bottom one, I look at the top one. That's how I remember it. You memorize it any way you want to. Yeah.
So that's independent of the inertial frame of reference?
That's right. Yeah, I didn't even say inertial, but you're exactly right. Everything we've done so far has been inertial, right? This is the first time we've talked about relative. And this is the definition of relative. And people freak out when they do relative because they don't understand it. It's that simple. You take the two velocities, you subtract them, you got a relative. Every time. It's that simple. Okay? So here's what I'm going to do. I want to stand on A and I want to look at the position of B. So I want B relative to A. How do you think I'm going to do that? I'm going to take XB minus XA. Ah, okay. So position of B relative to A is XB. What's XB? Yep, okay, so it's 2.5 T squared. Minus. Why minus? Because it's relative. B relative to A. Okay, minus. What's the velocity of A, or position of A? Negative 0.5 T to the fourth divided by 4. And what should that equal? It should be B relative to A. Okay, so you're standing there, you're looking at it. Where's B? The one I'm interested in, when I'm interested in it, where is B relative to me? 3. Is it positive or is it negative? Positive is this way, right? So am I interested in a positive B? I'm standing on A, right? Is it positive? B's over there, right? It was right here. It went here, correct? So I want this to equal positive 3. How many unknowns you have there? Just time. Can you solve it? Yes. Okay. And once you have that time, can you go find the velocities that they wanted? Okay. Problem solved, right? Can you solve a quartic equation like that? How are you going to do it? There you go. Mathematica solves it just like that. I did. It found, I'll post the mathematical solution. It finds times 4 times. How come 4? Yeah, because it's a quartic. And it comes up with a negative 1 second. Is that right? No. Comes up with 2 imaginary numbers. Is that right? And it comes up with a positive 1.06. What do you think of that one? Yeah. Okay, so you pick out the one that's right. The velocities are, well, I'm not going to give them to you because it's a homework problem, right? But anyway, you got the idea. Now, you don't have to use relative motion, but I think it comes out relatively easy, no pun intended, when you do relatives. Okay. Let me give you a real-world problem, real-world example of this kind of stuff. Oh, come on. Okay. We have a, I'm simplifying it a little bit, but let's say you have an aircraft, and on that aircraft you have a GPS. Who knows what a GPS is? You got them in your phone, right? Yeah. Global positioning system. And aircraft are now kind of switching over. FAA is having a lot of aircraft fly on GPS now instead of the old-fashioned things. But GPS isn't always there, and sometimes you get a failure or whatever. And so they would like to have, some people would like to have backup systems. And the backup system for airspeed. Airspeed is important when you're flying because if you don't have enough airspeed, the plane plummets, right? So anyway, what happens is they would like to be able to have an automatic method for calibrating a pressure transducer that gives you airspeed. What they have is a GPS, and they have a pilot who is licensed. One of the things they teach pilots when they get your license is you have to be able to fly your airplane at a reasonably constant speed around a circle at a relatively constant altitude. Okay? So what they want to do then is they want to be able to calibrate the pressure sensor. So here's what happens. You got an airplane. This is my version of an airplane. Okay? right? And you're in horizontal flight, and you're flying forward like this. So you have a velocity. Okay? You can measure that velocity with GPS. So you get the whole vector of this, and this comes off of the GPS. So you do this on a good day when you got good sunshine and you got good lock on your GPS and everything. You're comfortable with that. And then what you have is unfortunately you have a wind. Now you don't normally know where the wind is. I mean, you know it's about 5 miles an hour, 10 miles, whatever it is, 20 knots, but you're not sure the direction. The airport will tell you that, but as you go up through the atmosphere, it changes. The speed changes, and so does the direction. And so you really don't know that wind. But what you can measure, is you can measure the magnitude of the velocity across your wings from a pressure gauge, and that's the way they used to do it, right? And that's what holds the airplane up. It's the wind across the wings that give you the Bernoulli effect that holds you up. Make sense? Okay, so here's the thing. How would you fly in a circle, measure this, so you have a record of that, and measure this that's coming off of a sensor, and match up and say, okay, I know, because what you're going to do is you're going to get pressures here, and the greater the pressure, the higher the wind speed. Okay? But I don't know what the pressure is, so when I measure a pressure of 2 psi, is that 30 knots across the wing? You see what I'm asking?
What are you looking for?
I'm looking to calibrate that air pressure sensor, so I get the true wind speed, or true, airspeed.
So you don't know the pressure and you don't know the wind?
No, because, somebody put this thing on his airplane, he just went and bought it from Radio Shack, it shows it on there, how do I calibrate it? It's not quite that, but, right? So how do you do it? You know the GPS vector? You don't know the wind? What would you do? See, what you're looking for, this is relative, right? You're looking for the relative speed across your wing. Can you think about that? Give me a solution of the wind state. If you can, I will give you a homework grade. Okay. Think about that and see how you would use relative motion to try to figure out. You understand what I'm saying? You got the GPS vector, so you know how you're moving relative to the ground. You have a pressure sensor that is somehow related to the speed. So, for example, double the pressure, double the speed. Let's keep it simple. It's not quite that way. Double the pressure, double the speed. But I don't know 1 psi, is that 5 miles per hour or is it 10 miles per hour? I don't know. Get the idea? So there's a scale factor on the pressure. So how can I fly the plane in a circle and figure it out? And it has to do with the relative motion.
Don't you have to find that starting point first?
I don't know. You tell me. I don't know. I'm trying to give you a taste of the real world, right? And we're walking down a bit. Why would you ever need relative motions? Well, here's something that I've done. I don't know. Talk to these people. I'm your boss. Yeah? Your boss doesn't know squat. Don't ask your boss anything. They just want the answer. I just want. How would you do it? Talk with each other. I'm going to give you the pilot will fly in a circle at a constant speed, right? And he has a bearing, so he knows what he's doing. That's coming from the GPS. That's the ground speed, right? So you know that. And you know you're getting pressure, but two, is that 5 miles per hour or is it 10 miles per hour? I don't know. Big part? I don't know. Talk with everybody, find out.
What is the sensor telling you?
It's telling me pressure, and that is, let's say, proportional to the airspeed. The only problem is I don't know the proportionality constant. Right? So at 0 pressure, I have 0 airspeed over the wing. At 10 psi, it's either, let's say it's 20 miles per hour. Then if you double it, you'll double the speed. It's not true, but I'm keeping it linear, right? Because it's really a quadratic. All right, so you're trying to find out I'm trying to find out what's the constant proportionality that I should have on my gauge. Okay? And do we have time to really do the problem? Or? Okay, I'll work one out and post it. The other ones are like the guy rowing the rowboat and that's all going on.
Find the functionality of living okay. What is the answer? Yes.
Try it. Well, see, if I tell you yes, you go that way. If I tell you no, you won't go that way. If I say I don't know, you will discover it.
Well, because it's not dimensional, so it doesn't matter.
Go and learn, right? Go and, well, I don't know. Go and learn. Go and learn.
The only variables that we have for the airplane one is our velocity to the ground
Right.
and the pressure we have in the wing and how it's related to it when
Yeah, you have three things. You have the X and Y velocities along the ground coming from GPS. So you know you're going 2 miles east and 55 miles north, right? You know that. Then you will also know that the pressure is reading 2 psi, right? And if it read 4, that would be twice as much wind across it as 2. But I don't know how much is 2. Could it be 1 foot per second across my wing? In which case, double it, I have 2. You get the idea? Triple it, you get 3. Or is it half? And then I would have 1.5 and 4.5 or whatever it is. You see what I'm saying? So I don't know that proportionality. And I want the proportionality so that when GPS fails, I can look at the thing and go, I'm reading a pressure of 6. 6 times the proportionality constant is, I can still fly. Get the idea? So I want the proportionality constant so that when the GPS fails me, I can rely on the pressure. Okay?
On that we were just talking about, so you're flying in a circle, right?
Mm-hmm.